Until now, in what we were doing, we're assuming that we had one interest rate, or one force of interest, and that means interest rate was the same for any time in the future when the cash flow occurred, so any maturity of a payment. In reality, that's not the way it works. If you look at bonds that are zero coupon bonds, or pure discount bonds, zero coupon bonds, bonds that only make one payment at maturity, there's a pretty significant market of those for U.S. government bonds. Then you can see what interest rate you need to have for the whole time between now and the payment to get the price in the market equal to the to what you see in the market based on that interest rate. So you can read the interest rate from the price of a market based on that single payment that you have in the future that you know was going to be. And you can see that those interest rates are different for different terms. The yield curve, or term structure of interest rates, is that pattern of interest rates for different maturities, for discounting cash flows of different maturities. Now, the specific functional relationship between the time of maturity and the corresponding interest rate is usually called the yield curve. So it's a function that tells you what the interest rate is depending on maturity, while term structure of interest rates is the general description of the phenomenon of rates varying for different maturities. But you may hear both expressions roughly meaning the same thing. Now, typically, longer-term bonds have higher yields in reality. Such a pattern of interest rates is termed an upward sloping yield curve. If interest rates are the same for all maturities, we say that the yield curve is flat. And sometimes, rarely, but sometimes it happens that longer-term maturity interest rates are lower than shorter-term rates. We say then the yield curve is inverted. There are actually three ways to define the yield curve and the term structure of interest rates to specify what the interest rate is for various maturities. The first one assigns to each maturity date, each time in the future, the coupon rate of a bond of that maturity trading at par, newly issued bond. So you issue a bond right now. It has a specific maturity, say 10 years, and if you issue that bond with a certain coupon, it trades at par. That means basically that yield of the bond is the current yield rate in the market. Okay. That yield is then assigned to that maturity. That's the current yield for that maturity. And because this yield curve assigns to each time in the future the yield of the bond, it's called a bond yield curve. The second approach assigns to each maturity date the interest rate of a zero coupon bond, so no coupons this time, zero coupon bond with that maturity. So you have a zero coupon bond with a specific maturity, and you figure out from its price in the market what the interest rate is that makes the present value of its future single payment equal to the price that you observe in the market. Okay? The yield curve so obtained is called the spot curve, and the interest rates given by it are called spot rates. So spot rates are obtained from zero coupon bonds. Now, the third approach uses short-term interest rates in the future periods of time implied by current spot rates. And later on, you'll see that this actually is basically this gives you the interest rates that are embedded in short-term bonds, but purchases sold on the forward through a forward contract, but we'll get to that later. So a short-term interest rate, or a short rate, is an interest rate applicable for a short period of time. For example, 1 year or less, typically. Short rate basically means virtually always 1 year or less. And it could be also a theoretical concept of an instantaneous interest rate, which is basically the same concept as we learned before of this force of interest depending on the period of time where it varies. If we use the 1-year rate as the short rate for the purpose of deriving forward rates, we have the following relationship. And I'm sorry, I don't see myself saying clearly here, but we are defining in this process the forward rates. So let me stress this in a sense here. So if Sn, this relationship defines as if Sn is the spot rate for n years, and then if you invest $1 today, after n years you will have 1 plus Sn to the power n. And then the forward rates, called F1, F2, and so on, are the rates from time 0 to time 1, 1-year rate, which is F1, and then another one from time 1 to time 2, which is called F2 here. Another one from time 2 to time 3 will be called F3, and so on, up to Fn, which is from time n minus 1 to n. And it has to be this way that 1 plus S sub n to the nth is equal to 1 plus F1 times 1 plus F2 through 1 plus Fn. Okay? Then these are called the forward rates. Okay? We also, because of this formula, we must have that if you write the same formula for 1 plus S sub n minus 1 to the n, to the n minus first, sorry, if you divide the two, you will see that 1 plus F sub n has to be equal to 1 plus S sub n to the nth divided by 1 plus S sub n minus 1 to the n minus 1. And also note that F1 has to be equal to S1. Now the yield curve also can be studied for a continuously compounded interest rate, so the force of interest. In this case, the force of interest delta is treated as a function of time. And then we have a spot rate and a forward rate. If delta sub t is the spot force of interest for time t, so from time 0 to time t, and phi sub t is the instantaneous forward force of interest at time t, then the accumulated value of money through both has to be the same. And we look at the accumulated value at time t of a monetary unit, so like $1 invested at time 0, and it's going to be e to the delta sub t to the power t for the spot rate, and also e to the integral from 0 to t of phi sub s ds for the forward rate. Well, that implies that e to the t delta t is equal to e to the integral from 0 to t phi sub s ds, or, if you take the natural logarithm of both sides, t delta t is equal to the integral from 0 to t of phi sub s ds, so that delta sub t is 1 over t times the integral from 0 to t of phi sub s ds. So, if you recall this from calculus, this is basically saying that the spot rate for time t is the mean value of the forward rates between times 0 and t. And also, if you take this t times delta t equals the integral from 0 to t phi sub s ds, and you take the derivative of both sides and use the fundamental theorem of calculus, you will see that phi sub t is equal to t times the derivative of delta with respect to t plus delta sub t. Okay, that implies that that derivative is positive, then phi sub t is greater than delta t, because you get phi sub t from delta t by adding a positive number to it, and if it's negative, then phi sub t is less than delta sub t. But of course, positive, the derivative of delta, means that the spot rates are increasing with time. So what this is saying is that if the spot rate is increasing with time, then the forward rate is bigger than the spot rate. And in fact, the forward rate also increases in time, with time, when the spot rate increases with time, but it increases faster. And the second one says that if the spot rate is falling with time, so we have an inverted yield curve, then the forward rate will also be falling and faster. Let's look at a simple exercise of working with spot rates. for now. You are given the following information about risk-free zero coupon bonds. And let me stress, you really must understand this exercise, and the ones that follow, we'll do a couple more in a moment. This basically is the simplest but really the only heavily tested material on spot and forward rates. You must understand this, okay? I hope you understand it from this exercise, but of course you can email me if you have questions or send me a message in some way. But anyway, you are given the following information about the risk-free zero coupon bonds for maturities of 1, 2, and 3 years. We have the price per 1,000 par. So the bond pays 1,000 a year from now, and its current price is $962. The second bond is a 2-year bond, so it pays 1,000 2 years from now, and its current price is $916. And the third bond pays 1,000 3 years from now, and its current price is $864. Based on this, the first statement basically tells us that 1,000 is equal to 962 times 1 plus S1 to the power 1. And of course that tells us that the 1-year spot rate is the solution of this, which is 1,000 over 962 minus 1. So, and it comes out to be about 3.9501%, 3.9501%. Now for the 2-year spot rate, basically what this is saying is that 916 accumulated at the rate S2 over 2 years gives you $1,000 in 2 years, and we solve this for S2, and we get it to be equal to the square root of 1,000 over 916 minus 1, and comes out to be 4.48459% approximately. And for the third rate, basically what this is saying is that 864 accumulated at S3 interest rate over 3 years gives you 1,000. You solve this for S3, and it's equal to the cube root of 1,000 over 864 minus 1, and that's approximately 4.99342%. Notice that these spot rates are increasing with maturity here, and we kind of know what this means about the forward rates. Okay, so now we use the same data. I was supposed to calculate 1, 2, and 3-year forward rates. So the forward rate for 1-year periods from time 0 to 1, 1 to 2, and 2 to 3. Okay, for 1-year rates, if you just do 1-year rate, annual rates, then the first spot rate is always equal to the first forward rate. So the first forward rate is 3.9501% approximately. And then for the second one, it has to be this way, that 1 plus S2 squared is equal to 1 plus F1 times 1 plus F2. But we just figure out that 1 plus F1 is 1,000 over 962, so we plug that in. And on the other hand, 1 plus S2 squared from the previous exercise is 1,000 over 916. From this, we see that 1 plus F2 must be equal to 962 over 916, comes out to be about 5.02183%. And 1 plus S3 cubed, which we know from previous exercise to be 1,000 over 864, is equal to 1 plus F1 times 1 plus F2 times 1 plus F3. Notice this is basically saying that we get the same result by accumulating with the spot rate or accumulating with the forward rates, because forward rates are basically corresponding to, later on you'll see, purchasing today a bond that will start in the future and end later on in the future. So F2 is the rate for a bond that you buy now, but it starts at time 1 and it ends at time 2. So you get to invest in the first year bond with the rate F1, and when it matures, you put the money immediately into the second bond from time 1 to time 2, and then when that matures, you put money in this third bond. It goes from time 2 to time 3, and either way you should get the same result. But this is what this is saying. And of course we know what 1 plus F1 and 1 plus F2 are from previous calculations. We plug that in, and that gives us 1 plus F3 equal to 916 over 864, and F3 is calculated as about 6.01852%. And that, notice what happens here is that the forward rates are increasing, but they're increasing faster than the corresponding spot rates, which is a standard pattern. Now, in this next exercise, you are given that the current forward rate from time 0 to time 1 is 5%, from time 1 to time 2 is 6%, and from time 2 to time 3 is 7%. You purchase a 3-year coupon bond paying an annual coupon of 60 with the payment of 1,000 principal at maturity. If in 1 year the yield curve is flat at 7% for all maturities, what is the total return in percentage of this bond for the year from time 0 to time 1? Okay, so we begin by calculating the current price of the bond. We don't have the yield of the bond. We only have the forward rates. But the forward rates tell us what the present values of future payments are. How? Well, if we had the spot rate from time 0 to time 1, then we would just discount the coupon of 60 using the spot rate. But the spot rate for time 1 is the same as the forward rate for time 1, so 60 over 1.05 is the present value of payment of 60 at time 1. For payment of 60 at time 2, if we had a spot rate for time 2 and discounted using the spot rate, then we would take 60 divided by 1 plus S2 squared. But 1 plus S2 squared is equal to 1 plus F1 times 1 plus F2, so we can plug that in and get the answer. Because we know F1 is 5%, F2 is 6%, F3 is 7%. And then the third payment of this bond is 1,060. Coming at time 3, and if we discount it over 3 years, we can discount it by dividing it by 1 plus S3 cubed, but that's the same thing as 1 plus F1 times 1 plus F2 times 1 plus F3, which we see here. Okay, and we end up with the price being 1,001.13. Now notice this. If you took your financial calculator, take n equal to 3, payment equal to 60, future value to 1,000, and the present value will be negative 1,001.13. I'm sorry, if you put in the present value of negative 1,001.13 and tell the calculator to compute CPT IY, so interest rate, you'll get the yield of 5.96%. That will be IY result. And that's slightly under the coupon rate of 6%. Meaning that if you describe this bond not in terms of spot rates or forward rates, but if you just calculate its yield the way we did it before, that yield comes out to be 5.96%. And of course that means that the bond is trading at a slight premium because its coupon is more than the current market yield. At the end of the year, the bond will pay a coupon of 60, and its price at that time, well, all interest rates are 7%, so we just discount whatever is left in payments of the bond at 7% with appropriate terms. So 60 to be paid in a year and 1,060 to be paid in 2 years, and the present value comes out to be 981.92. So the bond is now at a discount because rates have gone up. So if the investor buys this bond at the beginning of the year, the payment for the price of the bond is 1,001.13. It's the payment to be made. And at the end of the year, that investor would get a $60 coupon plus $981.92 in the value of the bond. So a total of $1,041.92. Well, what's the rate of return if you spend 1,001.13 and you get at the end of the year 1,041.92? The answer is what you see here, 1,041.92 divided by 1,001.13. That ratio has to be equal to 1 plus the interest rate. So if you subtract 1 from that, we get the interest rate, which comes out to be about 4.07%. And notice what happened here. What's a positive interest rate? So is it good or bad? It's not that good because you can see from the problem that for the first year, the rate from time 0 to time 1, which was like the risk-free interest rate for that period, is 5%. So if this investor didn't buy this bond and speculate, but instead just put money in the bank, they would have gotten 5%. But instead, they played with the bond market and got 4.07. And in economic terms, that is kind of a loss because the money could be put in the bank and earn 5% there. Instead, it's earning less. The difference is called the opportunity cost. You effectively lost money by this speculation because you should have made 5%. It's no-brainer. It's easy. It's risk-free. And instead, you're speculating and earning only 4.07%. Not good. Because of these issues with immunization, the weaknesses I had mentioned to you, has been some thought given to improving it. And in 1990, Thomas Ho and then Robert Raitano in 1991 developed a multivariate generalization of duration and convexity. They replaced the single interest rate parameter I by a yield curve vector, I vector equal to I1 through IN, where the coordinates of the vector of the yield curve vector correspond to a certain set of key interest rates. For example, for a quarter year, half a year, 1 year, 2 years, 3 years, 4, 5, 7, 10, 20, and 30. The price function is then the price for this vector of interest rates. And instead of analyzing derivative with respect to one interest rate, one could use partial derivatives from multivariate calculus with respect to those I1, I2, and so on. Well, there's one objection that could be raised with respect to this approach immediately. When you have a function of two variables f of x, y, we assume that x and y are different variables. They don't depend on each other. And these interest rates are correlated. They depend on each other. If one rate goes up, generally other rates also go up. It's not always, because sometimes the yield curve inverts, but generally interest rates for various maturities are correlated. So this is imperfect, but it's a tool for studying sensitivity of a price to interest rates for various maturities. Then the opposites of the partial logarithmic derivatives of the price as a function of this vector of interest rates are termed partial durations or key rate durations. And the total duration vector is minus the price with respect to all rates, which is basically the vector of partial derivatives of p with respect to I1, I2 through In. So this vector is divided by the price, which is a scalar, that's number, a value of the price, with a minus sign in front of it. This is called the total duration vector. And you could also introduce the notion of directional derivative in the direction of a vector by multiplying the vector of partial derivatives by some directional vector v, and that's a dot product of vectors. The second derivative matrix can be defined, can be used to define total convexity, which is the second derivative matrix, which consists of all second mixed partial derivatives of p with respect to ik, ij, where this k and j are all numbers between 1 and n. This whole thing is divided by the price, so that in the matrix you basically have all these second mixed partials, each one of them divided by a scalar of the price. You can now view the surplus of an insurance firm as a function of the set of key interest rates chosen that for this consideration, so those I1 through IN, and use multivariate calculus for two immunization algorithms directly analogous to one-dimensional case. To protect the absolute surplus level, you set the first derivative, the gradient vector, equal to 0, but a 0 vector, of course it's a vector, and make the second derivative matrix of the surplus positive definite. To protect the relative surplus level, so the surplus ratio, you set these total duration vectors of assets and liabilities equal, and make the total convexity matrix of the surplus positive definite. And it's basically the generalization. It has its problems, as I mentioned before, but it's a generalized strategy of immunization. My feeling is that this topic is probably too complicated to be asked in any sophisticated form, but if they really want to get to you, they could ask a question like this one, which is simply a two-dimensional generalization of the approximation of how the price changes as a result of change in interest rate. So we would have, if you only use duration, the delta P over P is minus the duration times the change in interest rate. And of course, if you add convexity, it's 1 plus 1/2 convexity times the change in interest rate squared. But if we just look at the first term, linear term in that, there's a generalization for these multivariate durations for all the key durations. And let's look at an application of that, and you'll see the formula here. So you manage a bond portfolio for a life insurance company. You have observed that when the 1-year spot interest rate rose from 3% to 3.20% and the 10-year spot rate rose from 350 to 375%, notice that both of them go up, but not by the same amount, which is really the way most of the time things work in the bond market. Your portfolio lost 1% of its value. Lost value because rates went up. On the other hand, when the 1-year spot rate fell from 320 to 290 and the 10-year rates fell from 375 to 360, your portfolio gained 0.75% of its value. You made money because rates went down. And based on this, estimate the 1-year and 10-year key rate durations, which are also known as partial durations of your portfolio. So the key formula is what you see here, that delta P over P. In the one-dimensional case, it was approximately equal to minus D times delta I, but now it's minus D1 times delta I1, minus D10 times delta I10, where I1 is the 1-year spot rate and I10 is 10-year spot rate. Now you can calculate these with respect to spot rates or forward rates. It's really kind of an open definition, but spot rates are most popular. Okay, so if that formula holds, we just substitute the data given in the problem. We get minus 1%, that's a loss in the portfolio, if the 1-year rate rose by 0.20% and 10-year rate rose by 0.25%. That's basically written in the first formula. And then you have a gain on the portfolio of 0.75% if the 1-year rate fell by 0.30% and the 10-year rate fell by 0.15%. That's basically what the second formula says. Well, we solve this as a system of two equations with two unknowns, and we get D1 equals to 5/6 and D10 equal to 10/3.